Hello, I'm Kurt Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today we'll be working on Unit 12, Lesson number 3 on adding probabilities. So, as we continue to move along with our investigation and our study of both theoretical and empirical probability, we're going to get into more complex probability situations. All right? Don't forget fundamental definitions about sets, about how to calculate probabilities, about complements of sets and subsets, because as we continue to build up these mechanics, they will get a little bit trickier. All right, but let's jump into our first exercise and see what this lesson is all about. Okay, exercise number 1. Consider the spinner shown below that has been divided into 8 equally sized sectors of a circle. Okay. If the spinner is spun just once, do the following. In this experiment, we will let A be the event of rolling an even, and B be the event of rolling a prime number. Fill in the Venn diagram below with the actual numbers from the spinner. All right? Well, test your memory a little bit. See if you can remember what primes are. I think you know what evens are. And try to fill in that Venn diagram. All right, well, I'm sure you've worked with Venn diagrams before. We've worked with them a little bit, but what we haven't worked with yet are Venn diagrams that have this overlap. Now, evens are simple enough. 2, 4, 6, 8. We got them. The only question is, should any of those evens also be placed within the prime category? And the answer is yes. All right, the number 2 is both a prime and it's even. All right, so that's our circle enclosing the evens. The primes are 2, 3, 5, and 7. 1, as a reminder, is not a prime. All right, so it actually is going to go out here. 1, 2, 3, 4, 5, 6, 7, 8. Right? We have everything accounted for. We have the elements that are in the prime circle, the elements that are even in the even circle, the element that's in both, and one element that is in neither circle. All right? But that's it. That's the whole deal. All right? So, let's keep going and talk about what are known as intersections and unions. All right? Unions and intersections. All right, remember, we've talked about sets as being collections of outcomes, not outcomes, but collections of elements that satisfy well-defined criteria. All right. The union of two sets, A and B, is the collection of all elements that are either in one set or the other, or could be in both. So literally, in that diagram we had before, everything that's inside of those two is in their union. All right, so literally the union is what it sounds like. You take set A, you take set B, you squish them together. All right, you don't do double counts. Okay, so you don't have the element 3 and the element 3, right? You just have the element 3. All right, the intersection is also what it sounds like. It's all the elements that land in both sets at the same time, okay? And literally, it's this portion. That's the intersection. That's this guy, okay? So the union, we're putting two sets together. The intersection, we're finding all the elements that happen to be in both sets at the same time. Okay, the common elements. Okay? I'm going to clear this out, and let's practice a little bit with that. So sorry that I erased that first slide so quickly. Here's that first slide, right, with the evens in this circle, the primes in this circle, all right, and then the number 1 kind of hanging out here. From exercise 1, write out the following two sets, A or B, the union, which is symbolized by a symbol that kind of looks like a big U, all right? Well, the union would be, and you don't have to list them in order, but I'm going to, 2, 3, 4, 5, 6, 7, and 8, right? Literally, I just write down all those elements. And the intersection, which is symbolized by an upside down U, or what looks like an upside down U, is just 2. Now, exercise 3. From exercise 2, why is the equation NA or B equal to NA plus NB generally not true? What would be the correct modification to make it true? Use the last example to help explain. Now let's just first take a look at this thing. What does this really mean, right? What this is really asking is, why can't we figure out the number of elements in the intersection, in this guy, right, in the intersection, by just adding up the elements that are in the sets that form the intersection, the union. I kept saying the intersection. Why can't we find the number of elements in the union of two sets, put two sets together? Why can't we find the number of elements in those two sets by just adding the number of elements in the two sets that make up the union? Think about that for a minute. All right. Hopefully what you realized is because there can be an intersection. There can be elements you count more than once. So just think about this for a second. The number of elements in A from the last problem was 1, 2, 3, 4, right? The number of elements in B was 1, 2, 3, 4. And yet the number of elements in A or B was 1, 2, 3, 4, 5, 6, 7, right? So obviously 4 plus 4 doesn't equal 7, all right? So how can we change this to take into that account? Why are we getting 8 here, right? Why are we getting that? Well, we're getting it because we counted the 2 twice, right? So how do we modify this equation? Well, we could say, look, I'll take the number of elements in A, I'll add the number of elements in B, but then I'll subtract off the number of elements that are in their intersection because I counted those twice. So if I subtract them off once, then I've only counted them once. Does that make sense? This is a very, very important relationship, all right? The number of elements in the union of two sets is equal to the number of elements in the sets individually minus the number of elements in their intersection. That would certainly work here, right? Because we'd have 4 elements in A plus 4 elements in B minus the 1 element of intersection would give me the 7 elements in A or B. Okay, very important relationship, and we'll look at that a lot in the next problem. Okay, so pause the video now, write down anything you need to. Okay, let's clear this out and keep going. All right, exercise number 4. A small high school surveyed 52 of its seniors about their plans after they graduate. They found the following data and wanted to analyze it based on gender. In this case, if we pick a student at random, we can place them into one of 4 events. Let's make sure we understand the events. Okay, the events are that they're male, female, going to college, not going to college, right? Now make sure that you can really read this table, right? You've seen one of these tables before. I think it's called a bivariate table. It shows multiple kind of categories, right? And we can then take a look at how these categories interact. But this should be pretty easy. Take a look at letter A and see if you can answer all those numbering questions. And there's a lot of them, you know, because it extends all the way over to here. So see if you can answer all of those. Pause the video now. All right. Well, NM, we want to know the number of males. Well, here's the category of male, and here's the total number of males. So there's 30 of those. 30 of those things we call males. Let me make this eraser a bit bigger. All right. Number of females. Well, here's the females. Whoops. Here's the females, and in total there's 22 of them. Right? The number who are going to college. Right? Well, here's going to college, and there's 29 of those. Right? and the number not going to college. Well, here's the not going to college, and here's the number that are not going to college. That's simple enough. All right, so we've got like the number that fall into each one of these events. Now, how about the number that are male and going to college? See, this is an intersection, right? This is my intersection. And it's the intersection of two categories. The male category with the going to college category. And that is 16, right? Female and going to college, well, female going to college, that's going to be 13. Now here comes the tricky one. Female or going to college. Well, the total number of females is 22, right? So that's the number of females. The total number of people going to college is 29. But that would not be the number of people that fall in this union, right? What we're doing is we're looking at the union here of two events. The event that we've picked a female and the event that we've picked somebody going to college, or we've picked the event somebody going to college. But we've overcounted, right? Because what we need to do is we need to subtract, right? Number of females, number going to college. We need to subtract all those that we overcounted. And those are female and going to college. So we have to subtract off that 13. So when we do that, 22 plus 29 minus 13, we get 38 that are in that union. Okay? All right, let's take a look at letter B. What is the probability that a person picked at random would be a female who is going to college? Represent this using either a union or an intersection. Well, if we're talking about a female who is going to college, are we looking at female or going to college or female and going to college? It's an and, it's an intersection, right? So we want the probability that they're a female and going to college. This word and is very, very important because that's now going to be the number of females and college, that intersection, divided by the number in our sample space. Well, the number of females that are going to college is 13, and the number in our sample space is 52. So we get 13 over 52, or 0.25. Oftentimes, probabilities are expressed as decimals accurate to 2 decimal places, although 13 divided by 52 is exactly 0.25. Letter C. What is the probability that a person picked at random would be a female or someone going to college? Represent this using either a union or an intersection. Well, whenever we see the word or, that's a union. So female or going to college, that will be the number of female or going to college divided by the number in our sample space. But the number of females or going to college is 38. All right, divided by 52, which again expressed accurate to the nearest hundredth is 0.73. All right. Now, letter D says, explain why the probability of female or going to college isn't the probability that you'll pick a female plus the probability that you'll go to college. By the way, just take a look at that really quick. The probability that we would just pick a female is 22 divided by 52. The probability we go to college would be 29 divided by 52. And of course, if we added those together because they have a common denominator, we'd be good to go. We'd have 41 divided by 52. But we should be looking at 38 divided by 52, right? So why aren't those two equal? All right, and the reason is some people have been counted twice. Some people have been counted twice. It's pretty simple. By the way, that's not 41, it's 51. 51. Sorry about that. Oh, early. 51 out of 52, which isn't 38 out of 52. Letter E, fill in the general probability law based on D. Okay, and this is really cool. So the key here is that if I want to know the probability of a union, probability of A or B, I can find that by taking the probability of A and adding the probability of B, but then I've got to subtract off the probability of A and B. This is what I would call the double count. All right, and all this comes from our work on the front side of the sheet. All right, so the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. I can't tell you how important this one law is. This is exceptionally important. All right, exceptionally important. So pause the video now and think about this some. Okay, clear out the text. Let's do another problem. Exercise 4. A standard 6-sided die is rolled once, just once. Very simple experiment. It asks us to find the probability that the number rolled was either, important word, was either an even or a multiple of 3. Represent this problem and the sets involved using a Venn diagram. Even though you don't need it, verify the probability addition rule from exercise 4E. All right, let's draw a Venn diagram. Okay, now we've got two sets going on. We've got a set that represents evens, and we've got a set that represents multiples of 3. I'm just going to put down multiples. Yeah, maybe multiples of 3. Right, and here's my S. Well, multiples of 3, that would be 3, 6, and 9. And evens would be 2, 4, or 6. Whoops, I made a mistake there. It's going to be pretty hard to get a roll of a 9, right? Are there any that I kind of left out? Oh yeah, that's right. 1 and 5, right? They're hanging out here. So the evens are 2, 4, or 6, and the multiples of 3 are 3 and 6. All right. Now, if I want the probability that I get an even or a multiple of 3, well, I just have to count. I just have to count how many are in here, right? I just have to count how many are in the union, and that's simple, right? I mean, that's easy peasy. There's 1, 2, 3, 4. There's 6 total, so that's 4/6 or 2/3 or 0.67 or 67%, right? All good. 4/6, 2/3, 0.67, 67%, all good, right? Now it does say verify the probability addition rule. So the probability addition rule, let me call it E or M. That'll make our writing a little bit quicker. The probability addition rule would say, well, take the probability of E, add to it the probability of M, and subtract off the probability that a number is both even and a multiple of 3. Well, the probability that it's even, well, that's 3/6. The probability it's a multiple of 3, that's 2/6. And the probability that it's both even and a multiple of 3 would be 1/6, right? That's just the number 6. So you'd have 5/6 minus 1/6, and that would be 4/6, which is what we got right there. Now, a lot of students very understandably say, I don't need to know that probability rule. I just don't need to know it. I can always just say, well, okay, I know the evens are 2, 4, and 6, And I know the multiples of 3 are 3 and 6. I don't want to count the 6 twice, so I'll just do 2, 4, 6. That's 3 numbers plus the other 3. That's 4. I'm good. I don't need to know this rule. But watch how we can't avoid it in the next problem. Pause the video now, write down anything you have to, and then we'll take a look at it in the next problem. Okay, let's get rid of this. Exercise 6. Insurance companies typically try to sell many different policies to the same customers. At one such company, 56% of all customers have car insurance policies. So if I had my Venn diagram and I put a circle around car, let's say we had 100 people, 56 of them would be inside the circle that says car insurance. 48% have home insurance policies. So again, if I drew the circle and called it home, right, 48 out of those 100 people would be sitting inside of that circle. And 18% have both. Okay, so again, picture this, that Venn diagram, right? There's 18 people sitting inside of that intersection. Letter A says, find the probability that she or he has at least one of the policies. Okay, so in other words, we want the probability that they have a car or home, right? At least one means I could have a car policy or a home policy, or I could have both. All right, well, using the addition rule, that would be the probability that we have car insurance plus the probability we have home insurance minus the probability that we have them both. Whoops. And again, it's very important to do that subtraction because again, imagine 100 people. 56 of them fall inside of the circle that says C, 48 of them fall inside of the circle that says H, and 18 of them fall in that intersection, right, that slice. So the probability that they have car insurance is 0.56. I like working with the decimals here. Home insurance, 0.48. Both of them, 0.18. And that ends up being 0.86 or 86%. All right. Letter B says, find the probability that she has neither of the policies. So doesn't have car insurance and doesn't have home insurance. What would that probability be? Well, the probability that she has neither will be equal to 1 minus the probability that we just found. Right? This is the probability that they've got something. Car, home, both of them. To have neither of them means you have to fall into the category of the complement of this. It's the complement. Right? Neither is the complement of at least one. Of course, that's 0.14. That's a good way of writing it. Or 14%. All right. Think about letter B quite a bit. Think about why having neither policy is the complement of having at least one of the policies. Okay, pause the video now. Okay, let's clear it out. Okay, so today we saw that there are certain situations when you add probabilities. Specifically, when you're looking at the probability of a union of two events. Union means the word or. I'm either this or I'm that. The tricky thing, of course, when you're adding probabilities with unions is that there could be an intersection. There could be outcomes that fall into both events, that are in both events. And so when you're thinking about the number of elements in A and the number of elements in B, etc., you also have to take into account that there are elements in A and at the same time in B, and you have to subtract that off. All right, very, very important fundamental probability law today. So I'd like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.